In this video, I want to talk about the equations for lines and planes in space. So 3 space, 4 space, 5 space, whatever. First, let's start with what you know. When you're in R2, or 2 space, which is just normal for you, you have typically a line, something like that. It's y equals mx plus b. X tells you where along the line you are. Y stands for all the possible outputs. B is a particular point that you know you go through. Though you also have the point slope formula, you can use that to figure out the equation for a line. And m is the slope, so it tells you how far up and how far over to go. We've also talked about the slope being like a vector because we know that's a vector. And we tend to write the vector as, I shouldn't write m there, 1 comma m, because m is rise over run, y over x. It's easier just to write it 1m as opposed to like 1/2, 2, whatever. We're going to do the same thing in 3 space. We used x and y because we only had 2. Right? We had x and y, so it was okay to say x and y. But now that we have xyz, xyzw, LMNOP, QRST, we want to get away from using the alphabet. We want to start using subscripts. So, but for R3, we'll still stick with XYZ because that's what most people do. If I have a point and I know the slope, I can come up with the equation for a line. Slope being the direction, being the vector. So if I know I've got this point on my line, and this is some vector heading off to wherever it goes, if I just take this point or the direction vector, position vector of this, and add multiples of t, positive or negative, I will get the equation for a line. So let's say I know it goes to the point B1, B2, yada yada yada, Bn. And we're going to call the direction vector for that, just make it into a vector. B1, B2. As you remember from that 3 brown, 1 blue video, 3 blue, 1 brown, mathematicians are kind of fast and loose with going back and forth between points and vectors. Oops, I should pick one or the other. And let's say my direction vector, or my slope, we'll call, what's a good letter? How about m? So if I want the equation for a line in space, so R, in dimensions, I can write that as, well, I don't want to use y because that typically stands for the second coordinate in a thing. I don't use the x bar because that'll just mess you up. Typically what I've been seeing in the books that I've been looking through, they use r bar. Why r? I'm not really sure. So I need the point that I'm going through, so b bar, plus my slope, m. I need multiples of my line, so I'm going to multiply that by t. It's parametric. Who knew? Where t is any real number. T is an element of the reals. So, for example, let's say I have, I want the equation for a line going through these 2 points. I want to go through 2, negative 2, 5, and I want it to go through the point negative 1, 1, 7. Well, my slope vector, pick a direction. 2 minus a negative 1 is 3. Negative 2 minus 1 is a negative 3. 2 minus 3 is 3. Good. 5 minus 7 is negative 2. So, that's my direction vector. And I know it goes through either one of these points. Pick a point. What's your favorite point? R is equal to, I'm just going to pick this one. Call it 2, negative 2, 5, plus t times 3, negative 3, negative 2. And that is the equation, the vector equation of the line through these 2 points. What else can we do? We can also describe the line parametrically. We could say that x is equal to, well, I'm looking at this equation, I have 2 plus 3t. X is 2 plus 3t y is equal to -2 minus 3t, and z is equal to 5 minus 2t. Now that looks too messy. We can also just write it as 2 plus 3t, comma, -2 minus 3t, comma, 5 minus 2t. All legitimate ways to describe a line in 3 space. Yeah. Once you're in 3 space, or 4 space or 5 space, you have a couple more options. If you're in a plane, 2 lines are either, they can be parallel, pretend those are parallel, they can be the same line, or they can cross. So they either don't intersect, they're the same, or they intersect. But in 3 space, you have another choice. You have, where should I look? Let's see this up here. They can be parallel, they can be the same line, or they can be skew. Did I hit the one? Or they can actually, intersect or skew, where they're not parallel and they don't meet. You've got both possibilities. So we're going to keep that in mind when we look at some lines. So for example, let's say I have L1 is the line, I need to look up. Let's say I have L1 where x is equal to 3 plus 2t, y is equal to 4 minus t, and z is equal to 1 plus 3t. And my other line is x equals, now I don't want to use t because I use t up here, and they're actually different lines, and their t's and their s's might be different, just their slopes are different. So I'm going to use an s instead of a t. So my x here is 1 plus 4s. Y, I can't read over there. Y equals 3 minus 2s, and z equals 4 plus 5s. So let's look at these lines. For L1, I can describe this as my r is equal to 3, 4, 1 plus t times 2, -1, 3. And my second line is 1, 3, 4, and the direction is 4, -2, 5. These two vectors, these two slopes, are not the same. They're not multiples of each other. So I know that therefore these are not parallel. Why did I put t at the end of parallel? Parallel. Okay. So they're not parallel. Do they intersect? If they were to intersect, we'd have an x-coordinate, a y-coordinate, and a z-coordinate that were equal. So I would have, looking at my x-coordinate, I have 3 plus 2t would have to equal 1 plus 4s. Let's make that a real equation. So I have 2 is equal to 4s minus 2t. Divide by 2. Okay. Now let's look at my y's. Where's my y? I have 4 minus t has to equal 3 minus 2s. So simplifying this, I have 2s minus t is equal to -1. Okay. 2s minus t can't be 1 and -1 at the same time. Not possible. That means contradiction. So these are skew. Okay. Otherwise, I would keep going and try to solve for s and t, and that would tell me when, where, what, how they intersect. What about planes? We don't usually talk about the equation of a plane in 2 space because there's only one plane. What's the point? A plane is defined by 2 vectors. That's what these pens are. 2 vectors. Can you see that? 2 vectors. So if I know a point on the plane and I know 2 vectors in the plane, I can come up with the equation for the plane. So suppose we have a point. Let's call it what I did before, B. B point, B vector, I don't care. b1, b2, yada, 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 b sub n. And I have two vectors. Let's say my v vector, which is v1, v2, yada, 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 vn. And we have my u vector, u1, u2, un. So my plane, again, why should I use R or should I use P? Oh, it's R. R is my point. I need multiples of my V, and I need multiples of my U. So that's the equation for a plane. Even though it's called multivariable calculus, we tend to stick with just 1 dimension, 2 dimension, and 3 dimension. So just like a line, there's an easier equation to write a line in 2 space without all this vector shit. There's an easier way to draw a plane in 3 space with all this vector shit. So what you need to know is a plane in 3 space can be defined by a point on the plane and a perpendicular to the plane. This perpendicular to the plane is called normal. I have no idea why we have 3 freaking names for perpendicular, but normal is typically something that's perpendicular to a surface. So my normal is the perpendicular to the plane. If I've got that and I've got a point on the plane, then I can describe the equation for that plane. Let's say I know that R naught equal to, we're in 3 space, so I can say x naught, y naught, z naught is on your plane. And I know that n is normal to the plane. N has to be normal to all the vectors on the plane, to everything on the plane. And if I let R, so all R that satisfy this, make up our plane. I know that R minus R naught dotted with N, the normal, well, it's perpendicular. It's a vector on the plane, it's perpendicular, it has to equal 0. I can distribute the dot product, so I have n bar times R, dotted with R, must equal n bar dot R naught. So this gives me an equation for the plane. That's kind of a shitty one. Let's see if we can roll with this a little bit more. So suppose I know that n, let's say I know a little bit more about n. N is A, B, C. And my R naught I already gave you, and my, okay. So n dot R, well, R is just my generic X, Y, Z. So n dot R is AX plus BY plus CZ. N dot R naught is AX naught plus BY naught plus C Z naught. And they have to be equal. So we have this as AX, set these equal to each other, AX plus BY plus CZ is equal to AX naught plus BY naught plus CZ naught, which we could actually simplify or go back to this original one up here and say I have A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught. My voice is getting very sing-songy, I apologize. That would be the equation for the plane. What do I know? I'm going to give you an example of this. Let's say I have a point on the plane called 1, negative 2, 5. And let's say I know that a normal, I figured out a normal to the plane was negative 2, negative 3, 16. We're not graphing this. Why not? The equation for the plane containing that point with a normal to the plane that would be negative 2 times x minus 1 minus 3 times y minus negative 2 plus 2 plus 5 times z minus 16 equals 0. And that's the equation for a plane in R3. And I think that might be a good place to stop.